All right, we're going to talk about a brownout now, just to explain what it is. Now, there are a number of ways, there are different ways you can have a brownout, but the one we're going to talk about is the brownout that happens as a result of the loss of a single phase on the high voltage. But before we can get there, we need to go through a bit of a recap on transformers. Now, you'll remember, I've drawn one up here. You'll remember transformers from 2A. And basically, a simple transformer will consist of a winding that we energize, and through magnetic coupling, through the core of the transformer, it energizes another winding. There's no electrical connection between the two windings, but if we energize, we always draw the primary on the left and the secondary on the right. And if we energize this winding, this one becomes energized as a result. And of course, I've drawn this deliberately with the windings different. This one's the higher voltage, transforming it down to a lower voltage. And that's because there's fewer windings on that side. So let's just say, for example, that this was a 240 volt winding there, and we put 240 volts on it, and it produces 24 on this side. Okay, so that makes it a 10-to-1 transformer. So what that means is the secondary will operate on 24 volts when the primary is operating on 240. But of course, if you put 120 volts on here, you will only get 12 volts on here. Whatever you put on this side, you'll get 1/10 on the secondary. Okay, I'll distinguish that, P to S. And likewise, if we put 50 volts on there, 50 volts, we'll get 5 volts out. Right? You can think of any number. It doesn't work so much if you start to go above the 240. It'll still work, but there'll come a point where you've exceeded the voltage rating on this side, and you'll probably blow it up. The insulation won't be rated for the higher voltage you put on, and so there's a problem, of course. So, with that in mind, we can look at a three-phase transformer. So a three-phase transformer is the same thing, just 3 times. So if I put in 3 windings here, that's what your typical street transformer is going to look like internally, or as a circuit diagram. All right, and this side will be 11 kV. All right, and then this side, as you probably know, will be 400. All right, so we'll just put that in. So it's 11 kV, well, to 400. Some people still like to say 415, but the nominal voltage is 400 on the secondary. All right, and what happens is, again, this winding energizes this winding, and this one energizes that one. This one energizes that one, and they operate not completely, but almost independently of each other. Now, the trick with the transformers that you see, you can see hundreds of them out on the street, especially the ones that are mounted on poles. They're a lot easier to have a look at. And so you can see the 11 kV mains coming in. There's three 11 kV wires, and of course we know that our low voltage is 4. You've got the 3 phases and neutral. So that's the basics of that. Now the key point on all this is that all your distribution transformers, we'll abbreviate transformer, that'll happen a lot. All distribution transformers are connected delta star. All right, now that's delta, which is symbolized by the Greek letter delta, and Y, that represents star, because that's your star point in there. So we call them dy. No, that's not how it's written. call them DY11. Capital D for the primary, small y for the secondary, and 11. Well, let's not worry about the 11 now because they might be DY1, but the 1 and the 11 aren't important for the purposes of what we're doing here. Now, it's important to get what a delta connection is. So you've already, you would know a delta connection just in terms of a circuit diagram is drawn like that. Now, that's your delta, and we bring in our three leads like that. But that connection, you could see that it's almost a circle. You could redraw it as a circle. You could do your winding like that, and you could do another one, and then you could do another one, and they're in a circle, and you could bring your wires in like that. It's the same thing, right? And so the key point is we could connect it as a ring, and so that's what happens in here. That's what happens in the internals of the transformer. It's connected in a circle, right? So that circles back to there, and we bring in our phases like this. This is where you get your 3. Bring it in on the same side of each winding. So in this drawing, it's on the top side of each winding, and then of course the secondary is connected in star, as you know, and always you connect to the same side. So that might be A phase 1, that might be 2, that'll be B1, B2, and that'll be C1 and C2. So we star up all the 2s. All right, like that. And of course, we know that the star point is earthed, and that your star point is also the neutral. And then that's your phase, then that's your phase, and that's your phase. All right, so I've drawn it up a bit bigger, so let me get the other drawing. So hopefully this will help explain to an extent what I'm talking about. All right, so if we lose one phase on the high voltage, well, let's connect them all up in delta first and star. So the delta, as we said, is going to be connected in a circle. Join them all up together. So there's our high voltage connected in delta. Now our low voltage, we've starred all the 2s. Okay, we've starred the 2s together, and of course we earth that. That's earthed. And that is the neutral, so that goes out as the neutral. Neutral, and our phases go out like this. This will be C phase in blue, which is traditional, and B phase is white, but of course that wouldn't do any good, so I'll do it in orange. B phase, and A phase is red. All right, so that's A. And of course, coming in, as we said, we've lost a phase, so we'll bring in C phase to here. So we'll bring in our phases to the top of the winding. So our B phase is going to come in here. That's B, and we've lost A phase. All right, so let's just say we've got A phase here. We bring it in, but we lose it. All right, now what that does, because we've got these things connected in a circle, this is what happens. This winding is connected directly across B and C phase. So that's still got 11 kV on it. So that winding's okay. Well, it's in terms of it's still got full voltage. But these windings, have a look at what we've got here. We've got C phase coming in through that winding, through that winding. So it's like two windings in series. So it's effectively like this. There's B and there's C. It's like this. Winding, winding, and out. So they're sharing 11 kV. So that means they're going to split it's just a simple series circuit. They're going to split the voltage drop. So they're going to have about 5.5 kV on each of them. So that's what happens. All right, so now this winding's only being energized with half the voltage. So that goes down to 115 volts. And this one goes down to 115 volts. And so if your house is connected to C phase, you only get 115 volts. What I should have put in is I should have put in a few more earths here, because as we know, there are multiple earths. I'm running out of space there. There are multiple earths on that neutral. They're all over the place. You see them everywhere. And there's one at your switchboard too, hopefully. All right, and so if you're on B phase, you're still getting the full voltage energizing the winding you're on, so you're okay. You're going to get 230 volts. You don't even know that there's been a loss of a phase here. But of course, if you're on A phase, you do, because you go home or you're at home and the lights don't work if you've got compact fluoros and stuff doesn't work properly. But you probably find your TV works because they're so clever these days. They can work on reduced voltages, but there'll be a few things that don't work, and one of them might be your fridge motor. Your fridge motor, let's just say your fridge has fridge motor. The motor for your compressor has 8 times current on locked rotor. Well, you've reduced the voltage to half. Still, that's not enough torque to start the motor, so you're down to 4 times current on 115 volts. And the 4 times current, remember that your heat is I squared R T, so it's sitting there, it can't start, it's got 4 times the current, which is 16 times the heat. So that's what happens to fridge motors sometimes in a brownout. They're on half volts, it's not enough volts to start it, but it's enough, so it's sitting there on 115 volts on locked rotor, and it burns out. So that's how it happens. That's one of the ways, a common way to have a brownout is to lose a high voltage phase and 2 of your low voltage phases go to half. Half or approximately half. It's not exactly, it depends on how the load is shared between the phases, but that's the theory on it. So that's your brownout.